So yeah, now we'll be moving ahead. Moving ahead, we have this question number 14. What does this question number 14 say? Can 9 line segments can be drawn in a plane, each of which intersects exactly three others? How can we imagine it? The question is asking us, can 9 line segments be created on a plane such that each of them intersects at 3 points? What does it say? A vertex over here, a point over here, a point over here. These we consider to be as vertex. Vertex 1, vertex 2, and then excuse me, and then what will we have? 9 line segments. What can we infer from it? 9 line segments. Each of one. Now what? Now what? How can we move ahead? Can 9 line segments be drawn in a plane, each of which intersects exactly three other? Yeah, if it means that it, yeah, at most 18 vertices. That's what I can think of. At most 18, and each of them intersects at 3 points. Mm. So we'll draw it over here. 1 2 3 1 2 3 1 2 3. We had total of 6 edges till now. Each of them satisfy each other. We have 3 remaining. 1 2 3. We can clearly see that it's not possible. It is not being possible. But how can we prove it mathematically? How can we prove it mathematically? I don't know. Okay, let's move forward. We'll come to it later. So, part 3. Congrats, you have completed 2 parts. First one, which was the first part. The concept of graph. We have completed the concept of graph, in which we covered some interesting applications of how graphs can be used in real life. Second, what is second? Second, the degree of vertex counting the edges. We have completed graphs, degree of vertex, and counting of edges. Now we'll starting with the third part of this, that is some new definitions. In the country of 7, there are 15 towns. In a country of 7, there are 15 towns, each of which is connected to at least 7 others. Prove that one can travel from any town to any other, possibly passing through some towns in between. Oh, oh. So what was the data given over? In a country of 7, probably its name, right? Yeah. 15 towns are present. which are connected to at least 6 7 others. 15 towns are present which is connected to 7 others. How is it even possible? Like, at least it is said, right? It can be less. Prove that one can travel from one town to any other. At least it can be more, sorry. One can travel from any town to other, possibly passing through some town in between. Okay, as solution is present over here, we will be just going through the solution. Let us look at any two towns and suppose that there is no path connected between them. If we take a look at two towns and suppose there are no paths connected between them, this means that there is no sequence of roads such that end of one road coincides with the beginning of the next road. This means that mm, 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 mm. Let us look at any two towns and suppose there are no paths connecting between them. There, this means that there is no sequence of roads. There is no sequence of roads such that the end of one road coincides with the beginning of the next road, connecting the two towns. It is given that each of the two towns is connected with at least 7 others. Oh, at least 7 others, now I get it. So, considering itself, it can be there are 8, right? So, these 14 towns must be distinct. If any two were to coincide, there would be a path through them, or it, or there would be path through them, or it connecting the two given towns. Figure 33. So there will be at least 16 different towns. This contradicts the statement. Oh, power of limitedness. Power of limit. Right. The light in the light of the problem, we give two important definitions. A graph is called connected if any of its vertices are to be connected by a path, a sequence of edges of which begin at the endpoint of the previous one. And a closed path, a path starting and ending vertices coincide, which is called a cycle. A closed path is called a cycle, right? Now we can reformulate the results from the previous one. Yeah, if 1 and 2 are present like this, 1 2 3 4 5 6 7, right, okay. Prove that graph within n vertices with n vertices, each of which has a degree at least n by 2 by n minus 1 by 2 is connected. Fine. It is natural to ask how a non-connected graph looks. Okay, this is how a non-connected graph looks. Such a graph is composed of several pieces with each one of them can travel along the edges from any vertex to other. Thus, for example, a graph from figure 34 consists of 3 pieces, while the graph of figure 35 consists of 2 pieces. Okay. The pieces are called connected components. Each component is, of course, a connected graph. We know that the connected graph consists of single connected component. Question 14. Never Never Land. There is only one means of transportation, that is magic carpet. 21 carpets served the capital. Okay. Single line flies to Farwell. and every other city is served by exactly 20 carpets. Show that it is possible to travel by a magic carpet from the capital to Fawel, perhaps transferring from one carpet to another. Okay, Eulerian graphs. Let us look at connected components of the graph. Solution. Yeah, let us just understand the problem at first. In Never Never Land, there is only one means of transportation, that is magic carpet. 21 carpets lines serve the capital. Carpet lines serve the capital. Capital and 21 carpets line means total number of edges, which are the degree of the word capital is 21. Single line flies to Fawel. It is a Fawel single line. And every other city is served by exactly 20 carpet lines. Every other city is served by exactly 20 carpet lines. Show that it is possible to travel by magic carpet from capital to Fawel, perhaps by transferring from one carpet to another. I guess this would have solved it, but I think my interpretation of the question is quite wrong. Let us look at the connected components of the graph of the carpet line, which includes the capital. Let us look at the connected components of the graph of carpet. Nigga, what? Let us look at the connected components of the graph of carpet lines, which includes the capital. Mm-hmm. We must prove that component includes Fawel. Suppose that it does not, then there are 21 edges starting at one vertex and 20 edges starting at every other vertex. Therefore, this connected component contains exactly one vertex, one odd vertex. That is a contradiction. I didn't understood it. Methodological remark. The notion of connectedness is extremely important and it is used constantly in further work in graph theory. The important point in the problem solution of question number 16, consideration of connected components, is a meaningful idea often turns out to be useful in solving problems. Okay. I'm not understanding question number 17. I guess I'll just